Hi everyone, this is the next in the series of PowerPoints that I'm going to narrate for you. It's 13.3 electromotive force and internal resistance. And the first question I want you to consider as we go through is, do you remember that time when loads of Samsung 7s, I think, set on fire? I just wondered if you knew the reason why, and maybe you might know the reason why by the end of this slideshow. So, big question, why did some Samsung 7 phones set on fire? And the objectives you need to be able to do is be able to explain why potential difference of a battery or a cell in use is less than its EMF. EMF stands for electromotive force. Be able to measure the internal resistance of the battery and be able to solve internal resistance problems. So, EMF or electromotive force. So the definition, which you have to know, is electromotive force of a cell is the electrical energy per unit charge produced by the source. So that gives you the equation, electrical energy per unit charge. So the equation for EMF is, it's got this curly E symbol, epsilon in Greek letters. So EMF is equal to energy, divided by charge, and the energy is the energy that's being produced by the source. Okay, so if it's a cell, that will be from a chemical reaction, or it might be some other source, maybe like a solar cell or something. Units, EMF is measured in volts, electrical energy is measured in joules, and charge is measured in coulombs. So if you think of the cell as having that equation, then the rest of the circuit is separate. So the rest of the circuit you would refer, rather than an EMF, you would refer it as potential difference. So the potential difference across the terminals of the source is the electrical energy per unit charge delivered by the source when it is in a circuit. So it's sometimes called terminal potential difference. So if you think of EMF as the amount of energy that can be supplied, and then the terminal potential difference is the amount of energy that is supplied. And the equation for that is exactly the same. It's just that it uses slightly different letters. So V is the terminal potential difference. W is the work done, or the electrical energy delivered by the source. It's called work because that energy will be used in the circuit to do stuff. And then you've got Q, which is charge. So the equations are the same. Units are the same. It's just that this is how much you supply, this is how much can be produced, and that's how much you supply. And there is a difference between these two values, okay? How much you make is not the same as the amount that you can supply. So let's talk about why that is. And it's due to something called internal resistance. So here I've got a picture of a cell. You can see a positive terminal and the negative terminal. Now, the cell will use the potential difference it has, so the fact that there is a positive potential here and a negative potential here, it uses that idea to move the negatively charged electrons around the circuit, i.e. produce current. So you can see here that the little electrons move around of there to the negative. Now we know this isn't strictly true because the electrons will actually be attracted towards the positive, so electron flow is the wrong way around, okay? Anyway, this potential difference is what causes the electrons to move around the circuit. So if the electrons being repelled from the negative side and then they're attracted towards the positive side, but if we talk about the current, remember that's the opposite way around. If you think about just the electrons flowing, that's fine, they go around here, they're repelled by this side, head round, come back to the positive. But when they move through the cell, you've got to move them from a positive potential to a negative potential. And they won't like that because they're negatives. They don't want to move to that side of the circuit, to that electrode. So in order to do that, you have to make them move and you have to provide some energy. So in the power supply, you're forcing negative charge towards the negative electrode, and this requires a power supply to do work, so it needs energy. So when charged through the electrical source, this energy is dissipated through it, heating it up. So if we think about a battery will use chemical energy, a chemical reaction, to move the negative electrons to this plate. In doing that, they're doing work, and that creates heat, and that heat is dissipated through the battery. So you can feel this. If your phone is working and you're doing something on it, and it's working hard, you can feel it start heating up, okay? That might give you a clue to the big question. So let's have a look. So that, this heating effect is called internal resistance. There is a resistance to the electron flow here. So internal resistance, definition, you need to know the definition. The internal resistance of a source is the loss of potential difference per unit current in the source when current is passed through it. So if you think about this in terms of an equation, resistance equals potential difference divided by current, which comes from Ohm's law. So the internal resistance of a source is the loss of potential difference per unit current in the source when the current flows through the source. If you're not using your phone and there's no current flowing through it, it doesn't get hot, so there's no internal resistance. Okay, it's only when you're using the power supply. So we've got a circuit here. Here's the power supply. It's 9 volts. We'll look at the 9 volts in a minute, but we've just got a power supply. And next to it in series, you can see a resistor, little r. Both that power supply and the R are inside this dotted box. The dotted box means that there is internal resistance. So sometimes when you do electricity questions, there's no box. So you just ignore the fact there's internal resistance. But if there is a box, you have to say there's an internal resistance. Then here you've got a load, so you've got a resistor, something with resistance. And if it's a resistor in the circuit, it's got a capital R. And then the internal resistance is a lowercase r. And what you're saying is this power supply has the ability to produce 9 volts, but it has internal resistance. So it's going to lose some of that potential difference here. So what the circuit gets will be less than 9. So if we use V equals IR, we get this equation. V is now the EMF, so the 9 volts here, equals I, so that's the current, that's fine. And then your resistance, you've got 2 resistors in series. So even though this is inside the cell, it's still in series. And we know that series resistance, you just add them together. So that's here. We can, so you can use it like this, or you can substitute in the I, so you get IR plus IR. This IR will be the potential difference or the terminal potential difference in the circuit. Okay, so sometimes you can just replace that with V. So what you have here is the EMF is equal to terminal potential difference, the potential difference in the circuit, plus any voltage that's lost due to the internal resistance. Okay, so that epsilon symbol is EMF, IR, potential difference delivered to the circuit, sometimes called V, the terminal potential difference. And then you've got I little r, which is a potential difference lost in the power supply due to internal resistance. And that is sometimes called or referred to as lost volts. Okay, so let's have a look at an example. In the above example, we have an EMF of 9 volts here. The external resistor has a resistance of 100 ohms here, and there is a 30 milliamp current. And it says, what is the resistance of the internal resistor? First thing to do, write down what you know. So we know EMF, we know big R, and we know I. Don't forget to put the milli in. Select a good equation to use. So we want to find little r. So I'm going to use this one, just because it's nice and simple. So if we have a look, I'm going to rearrange it here because I want little r. So we need to get rid of the I. So take it to the other side and divide. And I'm left with big R plus little r. And then I need to get rid of this. It's not multiply here, they're added, so you just take it to the side, it becomes negative. So if you go little r is EMF over I, which was this bit, and then you take this to the other side, it becomes take away big R. Substitute the values in. EMF is 9, I is 30 times 10 to the minus 3, then I take away 100, which was big R, which is 200 ohms. Now, this example is in the book, so if you want to have a quick go, you can. I think it's in the book, sorry, it might not be. But if you're not sure, have another go at it, okay? Or use some different values here, make them up and have another go. Right, just having a very, very quick look at power. Power is equal to I times V. So if you think about in the circuit, then the voltage here will be the EMF. So if you want to find out how much power if you want to work out how much power a power supply has, then you would do its EMF times the current through it, which is there. And then going back to this equation here, so I've multiplied this by I. So if I multiply the rest of it by I, I get I squared R plus I squared R. And this is telling you that the power supplied by the cell here is the sum of the power dissipated by the resistive components in the circuit, which is this, and the power wasted by the cell due to its internal resistance here. I've only seen one question come up on this before, but it was a hard question. So just as a quick look, if you plotted a graph of the power delivered to the load, which is this bit, against the resistance of the load here, you get this shape here. And this is telling you that you get the maximum power delivered to the load when the load resistance is equal to the internal resistance of the source. So that's here. So when your load resistance big R equals little r, you get the maximum power. So say like your load resistance was 100 ohms, if your internal resistance was 100 ohms too, you'd get the maximum power. And that's really useful information when designing power supplies for electrical devices, e.g. speakers and amplifiers. If you can make your load resistance the same as what the internal resistance is, then you get maximum power. Right. For the next section, measuring internal resistance, there's a really big practical you do on it. So this video is excellent and it explains it all. So watch the video. Once it's ended, you can make notes from the screen, but there is some notes in your book as well on page 221. So choose either or and make some notes on it. And then try this question. Okay, I'll go through it on the next slide, but you can try it first on your own, okay? So you have a cell of unknown EMF, E, and an internal resistance, little r, connected in series with an ammeter, switch, a 10.0 ohm resistor, P. When the switch was closed, the ammeter reading was 0.40 amps. When P was replaced by a 5 ohm resistor, so you change this to a 5 ohm resistor, Q, the ammeter reading became 0.65 amps, so you change the current, which makes sense because this has a higher resistance than this, so the current is less and then it increases. It says calculate the internal resistance of the cell. So have a go yourself, write out what you know, write down the equation. You can have two equations, okay, one for P, one for Q, and then see if you can figure it out. If you're not sure, have a look on the next slide and I'll take you through it. So there's the question again. Let's look at circuit P. The EMF of circuit P will be I, big R, plus I, little r. We know the current, and we know big R, so 0.4 times 10. Plus, we know I, again 0.4, but we don't know little r. So we get 4 plus 0.4r. Fortunately, we've got two unknowns. We've got the EMF unknown and little r unknown. So we need a second equation. Second equation is for Q. Again, exactly the same equation, just changing the